Hello everyone, we are Team 9, also known as Team Don't Stop Believing, and this is our CHE470 final presentation, titled High Purity Cumene Production. My name is Yusuf Mohammed, and with me are my teammates, Ahmed Al-Mazroui, Jared Moore, Justin Wisniewski, and Jiho. And these are our team members. My name is Yusuf Mohammed.
My name is Jared Moore.
I'm Ahmed Al-Mazroui.
I'm Justin Wisniewski.
And I'm Jiho.
This presentation will discuss the process design, which refers to the BFDs of the unit operations used in our plant, as well as an economic evaluation of the feasibility of the plant. Finally, we will be discussing the recommendations on how to improve the process and what should be done in the future. The NetLion Chemicals R&D department has developed a new catalyst for producing cumene from propylene and benzene. This catalyst has a better selectivity to cumene than the competition, but potentially has higher capital and utility costs. The aim is to either enter the market using the better technology or to license the new catalyst to current producers. NetLion has identified the U.S. Gulf Coast as the location for the cumene production plant. Out of a total of 8 main and side reactions, 2 of them are related to cumene production. The primary reaction alkylates a single propylene molecule onto the benzene ring. One of the side products of the main alkylation is DIPB. In order to increase the plant's yield of cumene, a transalkylation reactor is used in which the transalkylation reaction occurs. Other side reactions occur within the system and result in the buildup of chemicals that need to be processed either by sending to waste or further purification and selling. The fresh benzene is to be provided by the company, and propylene is to be shipped via pipeline. The fresh benzene and propylene feeds are not pure and as a result contain a few impurities. The propylene feed is 92% propylene, 7% propane, and 0.5% ethylene and 0.5% butene. As for the benzene feed, benzene constitutes 95%, and the rest 4.9% is toluene and 0.1% is hexane.
The first part of our system involves the feeds. The benzene feed has a high amount of toluene, and that is too high for the cumene reactor. So we needed to use a separator to remove some of the toluene. This separator accomplishes 2 things. First, it allows us to send the stream 2, which is in the distillate, to the cumene reactor. And stream 3 of toluene is a high enough mass concentration that we are able to sell it and make some money off of that. The feed streams 2 and 4 are then combined in the cumene reactor with the recycle stream 24. What this does is this allows us to get the optimum amount of cumene from all of these reactions. The selectivity of the cumene is greatly increased by the recycle stream of 24. The other reactor that is very important in our system is the transalkylation reactor. And this is fed by streams 15 and 16. And in this transalkylation reactor, DIPB, which is side product of the Cumene reactor is reacted with benzene in order to produce more cumene. And as a result, this increases the selectivity, the overall selectivity of cumene, and allows us to reach capacity in our plant. Stream 22 is a purge stream, which is separated into both stream 23, which is the actual purge, and then stream 24, which is our recycle that goes back into the Cumene reactor. This accomplishes two things. It helps us to, again, reach our capacity by having stream 24 go back into the Cumene reactor and allowing us to recycle a lot of that benzene. Also, stream 23 is high in benzene, so we are able to sell that and make some money off of that as well. Coming out of our Cumene reactor and our transalkylation reactor, we have a series of separators that are used in order to purify our stream. Stream 12 is the next to last stream with our cumene in it, and it is then separated in what we call separator 7, and the distillate, stream 19, has our cumene in it and is at capacity. Stream 18 helps us to get rid of some of the other products that we have that we don't want in our stream because it takes us below the weight % that we need to sell the cumene. And it also removes some of the cumene so that we can stay at capacity and do not go over that.
The Cumene plant had two types of specifications that needed to be met in our design project. In order for our design to be feasible, hard specification had to be met, whereas soft specifications are specifications that are recommended to be met as it will increase the productivity of our design. I'll initially discuss all the hard specs that we met and then explain the soft specs that are not met. In this slide, I'll be explaining the Cumene product hard specs and its goals and the achieved results that we achieved. So in order to be able to sell the Cumene product, all hard specs had to be met. The purity of the product had to be at least 99.9 weight %, and our design produces 99.98 weight %. The capacity had a hard spec of 68,452 pounds per hour, and our design runs at 68,465 pounds per hour, making a difference of just 3 pounds per hour. The weight % of DIPB and toluene in that stream had to be less than 100 parts per million weight fraction. Ethyl benzene had to be less than 500 parts per million weight fraction, and N-butyl benzene had a maximum of 200 parts per million weight fraction. As you can see, our product has very few impurities, making it as pure as possible. Our alkylation reactor meets all hard specs except for the conversion and selectivity, which differs from the R&D data and had no impact on our process. The alkylation reactor had to run at a temperature lower than 400 degrees Fahrenheit, and we were able to keep the maximum temperature below that. The reactor feed had 4 main hard specs that needed to be met. The cumene weight fraction had to be lower than 1,000 parts per million, and the hexane weight fraction had to be lower than 3,000 parts per million, and toluene had to be lower than 1,000 parts per million. And as you can see from the results we achieved, all these 3 hard specs have been met. Another hard spec for this alkylation reactor was the benzene to propylene mole ratio, which had to be between 1 and 2 for the benzene. And in our design, we were able to achieve a feed ratio of 2. Not only our design meets the alkylation reactor hard specs, but it also meets the hard specs for the trans-alkylation reactor. A 6-mole ratio of benzene to DIPB needed to be met, and we were able to do that because of separator 5 that was working at a required efficiency. No more than 1 weight % were allowed to be fed in the trans-alkylation reactor of Cumene, and we are feeding 0.014%. Another hard spec was the N-butyl benzene had to be less than 20 weight %, and we were running at 0.01%. And all the heavies had to be less than 500 parts per million, and we only had 1 part per million. Unfortunately, we were not able to meet some of the soft specs, which is mainly due to the recycle issues and challenges we faced. Our 25% benzene and 45% propylene did not meet the required 96% minimum. Also, our fresh benzene waste is above by 38% of the maximum required. We were only able to recover 27% of DIPB and 63% of the cumene. Many of the chemicals that are involved in this chemical process are highly flammable, so we had to ensure that nothing gets too pressurized or too hot. Flammability of chemicals like toluene and benzene in our process was a huge issue because we could not run our process above a certain temperature, which made us limit the temperature of the separations and other units in the process. This meant that the columns and separators did not run as efficient as we could, and so we could not run them at a high temperature, making it more difficult to separate, and therefore we had to use more separators, which increased our capital cost. Several components of our design being used and produced in our plant have hazards associated with them and they are highly combustible. This means that we must be careful with how we handle them, and many safety measures had to be put in place.
So moving on to the economic analysis part of the project, the total capital cost of the operation was determined to be about $39 million. In addition to that, it was found that the byproduct gains trend in a steep upward fashion after initially showing basically no gain. Also, with a product selling price being at about 42 cents per pound, we were able to come up with an NPW that is equal to about negative $1.4 million or billion dollars. So next, the utility costs that are associated with the process that we designed comes to a total of about 35 million, more like 36 million, with the majority of the cost being taken up by the power required to run the process, as well as the cost of the medium pressure steam. Here, the major costs associated with running the production plant was determined to be coming from the raw materials vastly, and this is needed for the process to run itself, obviously. The utility and fixed costs, which also fall under the operation costs, together only take up about a very small portion, less than 10% of the overall operating cost combined. Moving on, the cumulative cash flow and the SG&A figures demonstrated that the trends increase over the next 20 years of operation, initially starting with no increase in the first few years. SGA especially experiences a steep increase before leveling off later down the line, while the cumulative cash flow experiences a very linear increase and then toward the end begins to level off.
So from our economic analysis, this plan will not be viable for the base case scenario, even though we met all the hard specs. The utility cost and the raw material costs are just too high. As a result, the after-tax rate of return is negative, which means that under the current condition, this plan will never make money in the expecting time period. The net present value is negative, which is negative $1,439 million. And this is the bar chart that shows what the profit will be in the 18 years for the base case scenario. Like we can see from the chart, it is clearly that the profit kept decreasing over the 18 years. Even though we can see the deficit for each year decreases over time, it is just unrealistic to build a plan that loses that much money. So for the plan to reach the 15% after-tax rate of return, the selling price of the Cumene must be higher than 101.78 cents per pound. From the chart, we can see that when the Cumene price is that high, after 13 years, the plant will start to make money. However, the current Cumene price is only about 42 cents per pound, so the possibility of Cumene price increased for about 150% is very low. And even if the price increased to that amount, the time for the profit is too long, which could cause other financial problems, unless suddenly we become the only supplier for the Cumene. Another way to get to 15% after-tax rate of return is to reduce the raw material price for benzene to 4.9 cents per pound. It will have a better profit than increase the Cumene price, since it will gain profit after 10 years. However, this change in the price is still very unlikely because the current price for benzene is 25.7 cents per pound, and I guess no one will sell benzene with that low price currently. Therefore, our conclusion is that this design is not profitable under the base case, and the ways to improve the profit for the plant are not very realistic currently. So our recommendation is that to not build the plant after the evaluation, unless there is an enormous change in the market that is in our favor. And that's all for our presentation. Thanks for watching, and hope you all good luck in this intense situation.
Do I stop recording?
Yeah.
Do you want to stop cloud recording? Yes.